Welcome back to the second part of section 1.1, Introduction to Problem Solving. What I had intended to mention in the first video was that also you should I'll have the manipulative kit that accompanies the textbook. And inside that manipulative kit, if you've not opened it yet, are things that look like this. You'll have these little envelopes, and you'll have these sheets that have things you can punch out, and then the envelopes are for you to store those. For that frog problem that I gave you, you could have also used some of these punch out cards. In fact, maybe go back and even try that. Lay out several of the green and several of the yellow, punch them out, and you can move them with your hands. The reason we do that is because touching things, right, gives us a deeper connection to the information of what we're doing. We can often recall things that we did with our hands differently than if it was just something that we saw or something that we heard. All of those methods are good, but it's important to engage them all, right? And so the more we can use our hands in addition to hearing and seeing, it's all good. So let's reflect on that activity. So I asked you to do the frog jumping problem and monitor your own thinking. Think about the strategies you used, what tools that you used. So I did the same thing, right? I did that problem, and I tried to really be conscious of what I was thinking as I did it the first time, right? So I saw it, I'm like, okay, I'm not going to think about this at all. I'm just going to do. And I think I jumped the green, and then I jumped the blue, and then I moved the green forward, and then I jumped the maybe the green forward here. I was like, okay, I'm doing great. Let's move the blue forward. And I did this. And I was like, wait a second. There's nothing I can do because I couldn't jump more than one green at a time. So I thought, okay, well, let me start again. Let's start with the green, and then we'll jump the blue. And I said, well, let's see if I try this time. Let me jump what did I do? I think probably did the green again. And then I said, well, let me jump the blue this time. And green. And I was like, oh, I guess I ended up with the same thing, but on the other side. So I started to notice what the problem was. I can never really end up with two of the same color sort of advancing across the board. And so then it's the process of thinking, well, how do I do this differently, right? How am I going to go about and do it differently? Noticing along the way when I get to one of those points, right? Like, okay, pause. If I jump the blue over the green here, will I then be stuck? If I jump the green over the blue here, will I be stuck? Well, yeah, I guess I already did, maybe. I don't know. So I start to sort of question myself as I'm going through the process, looking for flaws in my thinking, right? Flaws in my own thinking. Do the green, do the blue. Oh, well, what if I advance the blue and then I advance the green? So I'm not putting two of the same color next to each other. Let's maybe do it again. Okay, and then I stopped, right? I didn't just react. I'm like, okay, do I want to move the blue forward or do I want to move the green forward? And I thought ahead. If I move the blue forward and then jump it with the green, I'll end up with two greens next to each other. So I better do it the other way. Green, blue, and then I'm thinking, okay, this is gonna, I think, work out. Pause, make sure I do it correctly. Jump the blue. Okay. Don't want to put two greens next to each other, so I'll jump the blue, advance the green, jump, 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 move forward, right? And so there's this process of making mistakes along the way. Mistakes are essential to learning. We must make mistakes. We have to fail along the way, right? Our greatest growth, our greatest learning comes from our failures. And so we have to encourage that. We have to encourage mistakes to be made, but then reflect back on, all right, well, what did that feel like? What did it feel like? How did I actually go about overcoming that and persevering? Remember that word? We are persevering. All right. So let's get back to our note page. Let's share. Let's share. What am I sharing? Minimize you. Minimize you. All right. Share. Let me make sure this is working properly. Let's stop the share, reshare, and there we go. Okay, so now let's get into what is problem solving. Let's actually talk about what it means. Define some things. We need definitions. And so the first definition that I'm going to give you is, what is a problem? Like, how would you define a problem? The way we define a problem is this. A problem is something that exists when there's a situation you want to resolve, but no solution is readily apparent, right? We don't know what to do. That's a key, right? There's a situation that you want to resolve, but no solution is readily apparent. This whole section is about problem solving. So how do we define that? Problem solving is a process. It's the process by which the unfamiliar situation, referenced here, is resolved. A situation that is a problem for one person may not be a problem to someone else. That's a key idea about problem solving. So problem solving is the process by which the unfamiliar situation is resolved, okay? And again, what's a problem for one person is not going to be a problem for somebody else, okay? Another word, piece of terminology that we've already used in the first video was a conjecture, okay? A conjecture. So what is a conjecture? It's a statement that's believed to be true, but it's not yet proven. Mathematicians prove things based on foundational mathematical ideas or axioms, right? And so they build proofs to say, we can prove that this statement is always true using certain principles of mathematics. A conjecture is something that mathematicians think is true, or they can maybe show it's true in a lot of situations, but they haven't yet been able to prove it. An example of that is something called the Goldbach conjecture. Goldbach was a mathematician. Just to give you a little example, the Goldbach conjecture. It's one of the most famous conjectures, one of the most famous unproven mathematical ideas. And very old, very well known. It's an unknown or unsolved problem, right? So this is a mathematical problem. So the conjecture says that every even natural number. Do you know what a natural number is? Natural numbers are the counting numbers, not including zero. Natural numbers are 1, 2, 3, 4, etc. So that's what a natural number is. Every natural number greater than 2 can or is the sum of 2 prime numbers. Okay, every even natural number is the sum of 2 prime numbers. What are prime numbers? Prime numbers are numbers that have 2 distinct factors. They can only be they're only divisible by 1 and themselves, right? So prime numbers would include 2, 3, 5, 7, 11, 13, 17, etc. Right? Those are our prime numbers. So every even natural number greater than 2 is the sum of 2 prime numbers. So if we start with in greater than 2, 4, 6, 8, so all of these numbers, by this Goldbach conjecture, we should be able to take all of these numbers and write them as a sum, meaning addition, of two prime numbers. So 4 could be written as, well, 2 plus 2. 6 could be written as 3 plus 3. 8 could be written as 3 plus 5. 10 could be written as 5 plus 5. 12 could be written as 5 plus 7. 14 could be written as 7 plus 7, and so on and so on and so on. And so this has actually been shown to be true for integers less up to the number 4 with 18 zeros after it. So huge numbers, but mathematicians still have not solved this problem yet. It still remains a conjecture. So a conjecture is an unknown problem, it's a unsolved problem, something we think is true, right? But we don't know if that is actually true or not. So how do mathematicians go about solving problems? There was a mathematician, Polya, who years ago put together a 4-step process to solving problems. And this is still used, right? This is kind of a standard way that mathematicians solve problems. And so I'm going to work through these one by one. First, we'll just show you what they are, and then I'll go through them in a bit detail. So the first thing about solving a problem, the first thing you have to do is understand it. Understand the problem. You're going to have to know this problem solving 4 steps, right? You'll need to know these. You have to understand the problem, which means read it and comprehend it. Then secondly, you have to devise a plan, right? Plan how you are going to go about and solve it. Third is carrying out the plan, actually executing the steps of your plan. And then 4 is looking back and checking, verifying the solution. So let's talk about these one by one. So let's first talk about understanding the problem and what that actually means. Because there are lots of things you can do to try to go ahead and understand the problem. And so one thing that is a common strategy to understand is reread the problem. I tell my students all the time, never expect to know what to do the first time you read a problem. The first time you read a problem, it's just to like get an overview. What is this problem talking about? What is the main idea of it? You read it again to start to identify some key information. What's important in here? Read it again to start then formulating your plan. What might be a good strategy? Does this problem look like something that you've seen before? Can you connect it to something that you already know? Okay, so that's a great strategy. Read again. Read it 4 times. Read as many times as you need to, but never expect to know exactly what to do to solve it the first time you read it. Next, something that can be helpful in understanding the problem is start to draw a sketch, draw a diagram. This is one of my go-to strategies for me. I'm always sketching out pictures of things to just try to make sense of it and see it. Younger students specifically start to rely on tools, right? These objects, right? These manipulatives, these things they can start to touch with their hands. They like pictures. They use their senses, right? Their sight, touch, manipulatives to solve these problems. Visual aids, charts, diagrams, right? You have to connect things to pictures. On a personal note, I'll just talk about my son. My son, at the time I'm recording this video, he's an 8th grader. He's 13, and he's a great mathematician. He's won math competitions, and it's not because dad's a math teacher. It's I think has to do with the approach that I took when he was really young. When he was young, what I wanted to do is teach him how to visualize things. And so we talked about math all the time. I didn't show him how to like write out an addition problem and stack numbers and carry numbers. We didn't write. I didn't write stuff out numerically for years. He was probably in third or fourth grade before I really started to show him some of those things. I would sometimes draw pictures, but often I wanted him to be able to visualize things. And so we would just talk about math all the time, right? We would talk about it. We would talk about numbers. We would play with stuff. We would use manipulatives. And now he's got a great ability to sort of see problems on his own, right? And that comes from, again, not just necessarily writing out the numbers, but pictures and stuff you can actually move around with your hands. And then a couple other things you can do to help make sense of a problem is, keep doing this, keep making that mistake. Restating the problem in your own words, right? What does it mean in a different way? And making a reasonable guess at the solution to help become just familiar with the details of the problem. And so all of these things are important in understanding the problem first. You have to understand it before you can start to solve anything or try to solve anything. So the next step in Polya's 4-step process was devising a plan, right? Devising a plan. And when you devise a plan, it doesn't mean that's what you actually end up doing, right? I mean, you think about plans that you've made in your life. I just went on a vacation not long ago, and I had a plan for how things were going to go. And guess what? The morning that we were supposed to leave, we found out our flight was canceled. We had plans. They had to change. And immediately we had to solve the problem of getting a new flight a little bit differently. But it gives you a general outline of the direction that you want to go. This second bullet point, I think, is really important. The path from understanding a problem to developing a plan may be long, right? And people are impatient. Students, you may be impatient. You may want to just jump right to solving a problem. But it may take a while before you can develop this plan. Jumping right into a solution often leads to mistakes. So take your time, think critically, take the time to plan. And that third bullet point, right? Most interesting problems don't have obvious solutions. Mathematicians like things that are interesting, something curious, right? The Goldbach conjecture that I shared with you earlier. I'm sure somebody's out there right now trying to solve that problem. If they had obvious solutions, they wouldn't be interesting. And obviously, experience and practice are the best teachers. You're going to learn more from doing than by anything else. Number 3 in the problem-solving process is carrying out the plan. Right? How do we actually go about carrying out the plan that we set in place? So we do it, right? We as we go about it, we write down our steps. We write down our thinking, right? I don't like to use the phrase show your work. I like to use the phrase show your thinking, because everybody's going to think about things differently. And then you can go back and retrace your steps. What did I do? What was I thinking? If it was a complicated problem, it's going to take a lot of steps to solve. Can I go back and reanalyze my thinking? Remember the frog jumping problem? Remember how I had you analyze your thinking, right? If you've written things down, you can go back and analyze your own thinking a lot better. And that's a really important skill to develop. And then, I mean, and one other side note too, I, as a teacher, as a math teacher, have spent years trying to ask myself about my own students, what were they thinking? I read your tests, I look at your work, I grade quizzes, and I don't just run through it wrong, right, -3, -2. I spend a lot of time staring at your work, your thinking, your steps, to try to make sense of what you were thinking. It's how I have gotten much, much better as a math teacher. Because by doing that, by analyzing my own students' work and try to analyze what they were thinking, I then was able to understand the errors in their thinking and how lots of people were thinking about something incorrectly. Certain things that might seem obvious, and many teachers may go through and just assume that people know how to do. A lot of people don't. Some of them are very minor. So I'm always trying to look at my students' work and say, what were they thinking when they did this thing? What mistake might they have been made? What did they misunderstand? Finally, with carrying out the plan, it's so important to note that getting stuck is okay, right? You're supposed to get stuff wrong along the way. I always say sit, stare, and think, right? Don't feel like you have to be doing something. Just stare at it, reread it, stare at it, and think. Sometimes you also have to come back to problems later. Lastly, looking back. A lot of people skip this one, right? They skip it because they're done. You just want to be on to the next problem, right? But you have to look back. You have to verify. You have to check your solution. Reread the problem again, right? Refer back to the problem. Reread it. Does it make sense? Does the solution make sense? Did you actually answer the question that was posed? And then the interesting part can also be, were there other approaches to solving the problem besides the one that you did? Was there something else that now occurs to you as, oh, I could have also done it this way? When my dissertation, when I did my doctorate was in community college leadership, but I did it on something called number sense. You'll run across that term, number sense. And one of the core components of someone having number sense is to be able to solve a problem and know that the solution is reasonable, that it makes sense given the information in the problem. Okay. It's so important to note here that math is not, and math education is not just about getting the right answers to things. It's not about getting right answers. It's about mathematical thinking and learning how to communicate that thinking, right? There's only one way to really learn math, and that's to do it, right? There's only one way to learn math, and that is to do math. It can be frustrating. It takes patience. You have to take your time. You have to think through the problems. You have to not be afraid to try lots of different ways, get stuck, get unstuck, try a variety of new ideas, right? Wrong answers and what seem like unproductive approaches are just the best opportunities for learning that you have. And so that's it for this video. We will come back with the final video as we start to actually analyze strategies for solving problems.